Welcome to the next experiment. In this experiment, we will be using PSAT module of DSA Tools software. The objectives of this experiment is to create an SMIB system in PSAT, to perform load flow analysis for the system, to create an equivalent system by using reduction, and to perform short circuit analysis at a bus. The SMIB system to be modeled is shown in the figure. It consists of two generators. It consists of a fixed transformer and two lines. So the network data for the system is given in the table. The power flow data is also mentioned in table 2. The type of the buses: bus 1 is a PV bus, bus 2 is a PQ bus, and bus 3 is the infinite bus, it's a swing bus. So detailed procedure for the activities mentioned in the manual. Let us begin by doing it. So go to PSAT. You will get a window like this. To start with the project, click on File, New Project, click on Power Flow Data. Always start with filling the details of AC bus, because it is to the AC bus, it is the buses that the components are connected. So click on AC bus. So in order to add a new bus, click on Edit, Insert New Row. You can give the name of the AC bus, bus 1. You can specify the base kV. Bus 1 is having 24 kV as per the manual. Bus 1 is a PV bus having base kV of 24 kV. The voltage per unit is 1. It's a generator bus. Angle is kept as 0. Close. Edit, insert new row. We have bus 2. Base kV is 230 kV as per the manual. So it's a load bus. Voltage per unit, you can keep it as 1. Similarly, there is bus 3. Base kV of the bus is 230. It is a swing bus. You can see bus 3 is a swing bus. Voltage per unit as per the manual, it is 0.995. Okay. So next component is generator. Edit, insert new row. We have generator at bus 1 and bus 3. Let us start by filling bus 1. So see the generator power output 1998. The megawatt output is 1998. You can change the maximum to say 2000. MVR output is 666. Click on OK. Edit, insert new row. Bus 3, the megawatt output is minus 1997. The MVR output is this. You can change the minimum minus 2000. Okay, and click on OK. So generators are given. We don't have any load, you can skip the load. So the next we can give the line. There are two lines. So let us start by filling in the first line. The line is connecting buses 2 and 3. So click on bus 2 and bus 3. So from bus 2 to bus 3, the reactance we can give it as line number 1. Reactance is, you can name the line also. This is line 1. Okay. Edit, insert new row. We have this another line connecting bus 2 and bus. Insert new row. Another line connecting bus 2 and bus 3. So the reactance of the line is you can name the line as line 2. Click on OK. So the next component is a fixed transformer. Edit, insert new row. The transformer is between buses 1 and 2. Click on bus 1, bus 2. So So bus 1 and bus 2, in between bus and bus 2 we have a transformer. So the reactance of that fixed transformer is this. Okay, click on OK. So now we have given the data for all the components. So now we can solve for the power flow. So go to solution. Before solving, go to parameters. So here there are, click on solution algorithm. You can see the different algorithms like Newton-Raphson, fast decoupled, etc. So here we can choose any of the algorithm. For time being we are taking fast decoupled. We can keep this cities. Click on OK. Go to solution and solve. You can see below the fast decoupled solutions iteration 1, 2, 3 and 4. And the solution is conversed in 4 iterations. So this is how we solve for power flow. Now the solution for power flow is already updated in this power flow data. If you click on AC bus, you can see the per unit voltage as for PV buses we have already specified it as 1 per unit. So the angle will be calculated 25.45 degrees. So PQ buses we assumed by giving it as 1 per unit. So after solving the load flow it is 0.9773. So similarly bus 3 is a PV bus. We have already given fixed it as 0.995. So the values are updated here. Similarly the power flows of generators are also given. So in order to visualize this, we can draw a single line diagram. Click on file, new diagram, new single line diagram. Go to the bus tree. So drag and drop the buses. So you can drag the buses here. Bus 2 and bus 3. So this is our system. 2 generators and the power flow data is also updated. We can see the voltage magnitude 1 per unit, angle is 25.4543 at bus 1. Similarly for the other buses. You can see power is flowing, 1998 megawatt is flowing, 474 is the MVAR. So in order to animate the power flow, you can click on view and select animate power flow. So you can see how megawatt power flow is flowing. Similarly you can see for MVAR also, reactive power also. Besides this we can have different labels. Click on labels. You can see bus number, voltage magnitude, voltage angle, all these are checked here. That is why we are able to see these values. Okay, whatever one you want to see you can check and click on OK. So this is about solving power flow. So the next objective is to create a subsystem. So for that click on first you need to create a subsystem. The objective is to reduce the 3 bus system to a 2 bus system. Suppose we need only bus 1 and bus 2 and we need to create an equivalent of the remaining components. We use system reduction. So in order to do that, click on subsystem, select, you have to define subsystem first, define composite subsystem, and in this you have to mention which are the buses to be included in the subsystem. Here I need bus 1 and bus 2, so including bus 1 and bus 2. You have to save this file. Click on OK, close. So now we can go to solution, reduction or purge. So before doing reduction you need to save all the changes. So Click on OK. You have to save it. Control save. Save the power flow data. So maybe save. Yes. And also you need to save the single line diagram. You also need to save the subsystem files. Okay, now we have saved all the system. Now go to reduction or purge. Select the system you need. This is the system to be retained. The other system, for the remaining system, it will create an equivalent. So click on reduce. So the reduction is successful now. Reduction is completed. Close. Now go to file or to project. Go to project. Click on SMIB SLD. Now you will be having the buses which you specified, bus 1 and bus 2. For the remaining buses, it created an equivalent. So it may not show initially. So click on this bus 2 and drag from bus 2. So you can see whatever was after bus 2, the lines and the infinite bus got reduced to a single component. So this is about the system reduction. Also there is one more thing. The next thing we have to do is doing short circuit analysis. To do short circuit analysis, first of all we need to perform short circuit analysis for the complete system. So we need not, I am not saving the system, you may save it. So I am opening the file, open project, the previous complete file SMIB experiment. I am not saving the changes. So this is SLD. So if you need to create, if you need to study short circuit analysis, go to solution, short circuit, and you will get a window like this. So before doing short circuit analysis, you need to give some values for the impedance for the generators. So it was not mentioned previously. You can give it as 0.005. Similarly for the generator 2. Now you can perform the short circuit analysis. So you are performing it for the complete system. Fault, you need to decide if it is in polar or Cartesian. Okay, I am selecting polar. So you can see the fault current magnitude is 237.87. So in this case only triple line fault current is valid because we have only mentioned the positive sequence values. For we have not given any data for negative and zero sequence impedances. So only three-phase fault is valid. So you can manually verify how we got this values. So 237.87 is the fault current when the three-phase fault is happening at bus 1. Similarly, 135.95 is the magnitude of fault current when three-phase fault happens at bus 2, and similarly for bus 3. So that is about doing short circuit analysis. Also besides there are other things to be explored, like you can show contours. So it's like color options, like I will show you contour options. Here you can color based on the component parameter. Like if I am selecting bus voltage, if the value of bus voltage is 1.2 and above, it will be 1.2 per unit and above, it will be shown in red color. 1.12 and above, it will be yellow color. Like that we can give coloring. So you can also improve the range of influence. If I apply, it will be varying. Also you can change to power flow and apply. You can see if power flow is around 2000 megawatt, it will be in red color. So here the power flow is around 1998, so it is shown in red color. Similarly, let's say power flow through line 1 is 1300 around, so it will come in this green color. So we can give such coloring options also. These things can be explored. So that's all about this activity. Thank you.